Welcome to the Deep Dive. We're here to unpack the information you share, really get into the details, and figure out what matters most.
And today we're looking at something pretty ambitious in AI.
Yeah, building systems that can tackle really complex tasks. Think advanced robotics, things that need a lot of steps, maybe learning from huge data sets.
Right. And the main tool people look to for this is reinforcement learning, RL. Now, usually RL learns by interacting in real time, but there's this big push now for offline RL. The idea here is you learn just from data that's already been collected, no live trial and error.
It's like teaching a robot by showing it tons of videos instead of letting it, bump into things itself.
Exactly. Saves a lot of broken robots, potentially.
Right. And the big question for us today, really sparked by this new paper from Park and colleagues, Horizon Reduction Meets RL Scalable, is can we take these standard offline RL methods, feed them way more data, give them tons more compute, and just scale our way to solving these super complex problems?
It's the scaling dream, isn't it? We've seen it work so well in language models, in computer vision. You just add more data, bigger models.
And performance goes up.
Yeah.
You'd absolutely expect it to work for RL too.
You would.
But, and this is the core surprise here, the research found that for the standard algorithms, just piling on data, even 1,000 times more, wasn't the answer. They stalled.
They hit a kind of ceiling.
Yeah, a fundamental wall. So why did they hit that wall? And what does actually unlock the scaling? That's what we're digging into.
Okay, let's unpack that problem and the surprise finding.
So like we said, NLP, vision, bigger models, more data, more compute, better results. It's almost become a law of modern AI.
It's been the driving force behind a lot of breakthroughs, for sure.
Definitely. So these researchers, they wanted to really put this idea to the test for offline RL. And not just on any tasks, but on ones needing really complex, long sequences of decisions, what people call long horizon tasks.
Yeah, tasks where you need to plan many steps ahead accurately.
And they didn't mess around with the scale. They generated data sets with up to 1 billion transitions.
1 billion. Just for context, typical offline RL research might use, maybe 1 to 5 million transitions?
Exactly. So this is like 1,000 times bigger, a massive leap in scale.
Truly massive for this field. And they targeted some known hard tasks from the OG bench suite, things that standard methods, struggled with or couldn't solve at all with the usual data sizes.
Can you give us some examples?
Sure. There was cube-oct tuple, which involves manipulating 8 cubes precisely, very tricky. Then combinatorial puzzles like puzzle 4x5 and puzzle 4x6, think complex versions of Lights Out. And also humanoid maze giant, a really tough navigation task for a simulated humanoid.
And they picked the hardest versions of these, right, to really push the boundaries.
They did. And critically, they tried to simplify other things. They used low-dimensional state information and gave the AI clear goals. They stripped away challenges like complex visual processing or gaps in the data.
As they could isolate the core problem.
Exactly. They wanted to focus purely on, can these algorithms handle the sequential decision-making challenge over a long horizon if we give them more than enough data?
They set it up to give the algorithms the best possible chance, aside from the task's inherent sequential difficulty.
Pretty much, yeah.
Okay, so the moment of truth. They take standard offline RL algorithms, things like IQL, SAC, plus BC, CRL, FlowBC, and run them on these tasks with this enormous data set. What happened?
Well, this is the surprising part. The core finding was stark. These standard methods just struggled to scale.
I didn't see that performance boost.
Not really, not consistently. Performance often flattened out, hitting a plateau well below what's considered solved or optimal, even with the full 1 billion transitions.
Wow.
Yeah, and get this. None of the standard methods could solve all 4 of these challenging tasks. And for cube-oct tuple, that really complex manipulation task, they all basically failed completely, couldn't get any meaningful progress.
So throwing 1,000x more data at them didn't overcome the fundamental difficulty. That really goes against the scaling hypothesis we see elsewhere.
It does. And naturally, they thought, okay, maybe the models aren't big enough, or maybe we need different hyperparameters.
Right, the usual suspects.
So they tried making the neural networks much bigger, up to 35 times larger, hundreds of millions of parameters. They fiddled with learning rates, target network updates, trained for way longer.
The standard toolkit for trying to boost performance. Did any of that work? Did it unlock the scaling?
According to the paper, not really. These efforts gave maybe small bumps here and there, but No substantial general improvement across the board, especially on the hardest tasks,
Well,
which strongly suggested the problem wasn't just about network size or tuning. It pointed towards something more fundamental about how these algorithms learn, especially when faced with these really long sequences of actions.
right. So if it's not just data or model size, what is the fundamental issue? This is where the paper points to the curse of horizon.
Exactly. And this curse affects the algorithms in two key ways: how they learn the value of being in a certain state, and how they learn the actual policy, meaning what action to take next.
Let's break that down. Start with value learning. A lot of these methods use temporal difference learning, TD learning. How does the long horizon mess that up?
Okay, so TD learning estimates the long-term reward you'll get from a state. It does this by looking at the immediate reward you get, plus the estimated value of whatever state you land in next.
Makes sense.
But here's the catch. That estimated value of the next state isn't perfect. It has some error, some bias. Now, if your task is short, maybe that small error doesn't matter much.
Okay.
But on a long horizon task, where you might need to look ahead hundreds, even thousands of steps, you're essentially chaining these estimates together. The error from one step gets baked into the estimate for the previous step, and that error gets baked into the one before that.
So the errors just accumulate.
They accumulate, exactly. They compound over the length of the horizon. A tiny bias early on can snowball into a massive error in your final value estimate for a state far from the goal.
Like a game of telephone for reward signals.
That's a good way to put it. And this is a key difference compared to, say, predicting the next word in a sentence like large language models do. That's more like a supervised learning task at each step. It doesn't have the same kind of recursive dependency where errors inherently compound over the full sequence length in the same way value functions do.
To really nail this point about value error accumulation, the researchers used a clever little test case, didn't they? The combination lock task.
Yeah, it's a great didactic example. Imagine you have to input a very specific sequence of actions, like numbers on a combination lock. Let's say it's a long sequence. You only get the reward right at the very end if you get the whole sequence correct.
So the agent has to learn this precise, potentially very long chain of actions.
Exactly. And they compared standard TD learning, specifically one-step DQN, which looks just one step ahead, versus a version using n-step returns, 64-step DQN, which looks 64 steps ahead for its value update.
How did they stack up?
The difference was really clear. The standard one-step DQN's performance dropped off much more quickly as the required sequence length got longer. But the crucial part was why. Even when the error in predicting the very next step's value, the TD error, was similar between the two methods.
Okay.
The one-step DQN had much, much larger errors in its overall value estimate, the Q value. And these total value errors grew significantly the further away a state was from the final goal.
So that bias accumulation was clearly visible. The longer the effective horizon back to the reward, the worse the estimate got for the standard method.
Precisely. And just like on the big, complex tasks, they found that tweaking things like model size or learning rates for the one-step DQN didn't fundamentally fix this accumulation problem in the combination lock experiment either.
Wow. So that really highlights the limitation of standard single-step TD learning for long horizons. The n-step approach helps by reducing how far back those errors have to propagate in one go.
Exactly. Errors only compound over n steps, not the potentially vast entire horizon.
Okay, so that's the value learning side of the curse accumulating bias. What about the other side, the policy learning?
Right. So even if you magically had a perfect value function, knowing exactly how good each state is, learning the actual policy, the mapping from state to the best action can still become incredibly hard as the horizon grows.
How so?
Think about it. If you're very far from the goal, figuring out the single best immediate action that will eventually lead you down a long, complex path to success, that's a really complicated function to learn directly. Mapping current state to optimal first step of a 1,000-step sequence is tough.
You mentioned the paper makes an analogy to language models.
Yeah, it's like asking an LLM for just the final answer to a multi-step math problem without it showing the intermediate steps, the chain of thought. Breaking the problem down makes it easier.
Oh, okay.
And that's where hierarchical policies come in for RL. Instead of one giant policy, you might have a high-level policy that chooses intermediate goals or sub-goals. And then a low-level policy learns the simpler task of reaching those nearby sub-goals.
So you're breaking the long journey into shorter legs.
Yeah.
Reducing the policy's effective horizon.
Exactly. You structure the problem. Learning how to get to the next sub-goal is usually much simpler than learning how to get all the way to the final goal from here.
Got it. So the cursive horizon hits both value learning, bias, and policy learning complexity. And the proposed solution, based on all this, is
Horizon reduction, actively using techniques that shorten the effective horizon the algorithm has to worry about, either for values for the policy or ideally both.
so they tested this, applied these horizon reduction ideas to those tough benchmark tasks.
They did. They looked at several approaches.
What did they find? Did reducing the horizon help?
Yes, significantly. Just tackling the value horizon, using things like n-step returns. They tested a method called n-step SAC plus BC, showed much better scaling and reached higher final performance levels compared to the standard SAC plus BC on many tasks.
So just fixing the value bias part gave a solid boost.
It did. It directly addressed the accumulation problem we saw in the combination lock. Then, tackling the policy horizon with hierarchical methods like hierarchical flow BC, or another one called HIQL, also led to big gains.
Especially on those tasks where the standard methods completely failed.
Right, particularly on cube octuple. The standard flat policies couldn't even get off the ground there, but the hierarchical ones started to actually learn something meaningful. It suggests you really need that structured approach for complex manipulation.
Okay, so reducing either the value horizon or the policy horizon helps. What about doing both at the same time?
That was the hypothesis that tackling both should be the most effective strategy, and that led to the methods proposed in the paper, Sharsa and double Sharsa.
Sharsa's state high-level action rewards state high-level action.
Okay.
What's the architecture there?
It combines ideas. It uses a hierarchical policy learned with hierarchical flow BC, and it uses n-step Sarsa, which is another TD learning variant, generally simpler and sometimes more stable than Q learning, to learn the value functions.
Simpler components, maybe less tuning needed.
That seems to be part of the design philosophy, yes, trying to build something effective but also scalable in terms of implementation and tuning.
And how does it choose those high-level actions, the sub-goals? You mentioned hierarchy.
It uses a technique called rejection sampling. Basically, it generates a few candidate subgoals using its high-level policy, and then it uses its learned value function to evaluate which of those candidates looks most promising. It picks the best one according to the value estimate.
Interesting. Why rejection sampling instead of, say, using gradients?
The paper notes that rejection sampling worked particularly well, especially on tasks like the puzzles, which have discrete elements in their state. Trying to push gradients through for subgoal selection was less effective there, whereas sampling and evaluating just worked better.
Okay, makes sense. So the grand finale. How did Sharsa and double Sharsa perform on those really challenging large-scale tasks?
They showed the best overall scaling behavior. And critically, they were the only methods tested in the paper that managed to achieve non-trivial, learnable performance across all four of those really hard tasks, including cube octuple.
Wow. So they actually made progress where the others stalled completely.
Exactly. Now, they didn't necessarily reach 100% success everywhere, even with 1 billion data points, but they clearly demonstrated an ability to benefit from the massive data scale in a way the standard algorithms just couldn't. They showed much better scaling properties.
That really validates the core idea then. Standard methods choke on the horizon length, but explicitly reducing that horizon, especially combining value and policy reduction like Sharsa does, is the key to unlocking scaling with data.
Precisely. The evidence seems pretty strong. The cursive horizon looks like a genuine fundamental bottleneck, and horizon reduction appears to be a necessary component for scalable offline RL on complex, long-sequence tasks.
Did they mention any other interesting findings, maybe from ablation studies?
Yeah, a few supported the design choices. They found SARSA worked well for value learning, maybe better or simpler than Q learning in this setup. Using a specific type of loss function, binary cross-entropy, for the values was beneficial. And as we mentioned, rejection sampling outperformed gradient methods for extracting the high-level policy.
Okay. So zooming out, what's the bigger picture here? What does this research imply for the future of RL?
Well, the main takeaway is pretty clear. Scaling laws aren't automatic for offline RL like they might seem elsewhere. For complex, long-horizon problems, standard algorithms hit this cursive horizon wall.
Right.
But the good news is that techniques explicitly designed to reduce the effective horizon, like hierarchical policies, n-step returns, and particularly combinations like Sharsa, can break through that wall and enable much better scaling with data and compute.
Though, as you said, even Sharsa didn't achieve complete mastery on all tasks despite the billion data points.
Correct. It's a significant improvement, but not a silver bullet yet. The paper acknowledges limitations. Current hierarchical methods help, but they don't fully solve the underlying TD error accumulation. and methods that work best when the dataset already contains reasonably good short-term behaviors to build upon.
So where does research go from here? What are the open questions?
The authors lay out a few key directions. Can we develop methods that perhaps avoid TD learning altogether, bypassing the accumulation issue? Can we build deeper hierarchies beyond just two levels effectively? Is this curse of horizon something we can fundamentally solve? Or is breaking problems down hierarchically always going to be necessary for complex tasks? Big questions.
And this work also has implications for how we even evaluate new RL algorithms, right?
Absolutely. A huge point they make is that testing new offline RL ideas only on the standard smaller benchmarks might be misleading. It doesn't tell you if they can actually scale.
Because those benchmarks might not be complex or long horizon enough to reveal these bottlenecks.
Exactly. So they argue compellingly that new methods need to be evaluated on large-scale data sets and genuinely challenging long horizon tasks, like the ones they developed. And crucially, they've open sourced their tasks, data, and code to help the whole community do that.
That's fantastic. A major contribution to enable more rigorous testing of scalability.
Yeah, it really raises the bar for demonstrating progress in offline RL, pushing towards tackling real complexity.
So wrapping up, the core insight for you, the listener, is this. Scaling offline RL for complex tasks isn't just about throwing more data at the problem. The length of the task, the horizon, is a critical, often limiting factor.
It's the bottleneck. And techniques that actively work to reduce that effective horizon by structuring the value learning or the policy itself seem essential for making progress on the really hard stuff.
It leaves us with that provocative thought. Is the future of highly capable RL inevitably tied to hierarchical decomposition, breaking big problems into smaller ones? Or is there another path waiting to be discovered?
A fascinating question for the field moving forward.
Definitely something to keep thinking about. Thanks for unpacking all that with us.
My pleasure. It's really interesting work.
We hope this deep dive gave you valuable insights into where AI research is heading. Keep learning, keep questioning, and we'll catch you on the next deep dive.